Section 8.4 of your textbook is all about corrosion and explosions. So the first thing we're looking at is corrosion. Corrosion requires water, oxygen, and an electrolyte. So if this is a metal tool that you left out in the rain, you would notice that you'd start to see some rust. Now the water can perform kind of like a little protective barrier, but right along where the water is touching it, you're going to see a lot of rust. And so basically that iron is going to mix with water on the edge, and it's going to mix with oxygen, and it's going to form that iron oxide that you see in this equation. Alternatively, then, that iron oxide could be converted into a different form of iron oxide. So this here is iron 2 oxide, notice the 2 here, and this is iron 3 oxide, notice the 3 here. And so what would be happening here is the iron, which is iron 0, gets oxidized to iron 2 plus. And it reacts with this oxygen, it reacts with the water, all of this chlorine and the salt. They help facilitate that reaction. They help with the charge transfer, and it forms this rust. Yay, rust, which is what makes your tools no longer be shiny, but it starts to corrode. It leads to them being not as strong, and they can break apart. Or after this iron oxide is formed, this form of iron oxide can go further and react more with water and more with oxygen to form iron 3 oxide, where now it's been oxidized even further. So in this case, if you've got water, you've got oxygen, you have a metal, and then you also have an electrolyte, you can get oxidation occurring, or in this case, rust. You may be thinking, well, what about the Statue of Liberty? I don't see rust all over the Statue of Liberty. Well, you still see oxidation. So in this case, this is copper. The statue was copper. So when it first was made, it was probably a nice pretty sheen, that shiny copper that you're used to seeing for some of your nice pretty brass pennies. Which, pennies are zinc and copper, so there's a little bit of both of them in there. But you've got nice shiny copper. But then when it got shipped to the United States, it was probably already a dark brownish red. But now it's this pretty bluish green color that you see on the screen. And what that is that's copper oxide. And so copper oxide is going to have more of the green color of the copper 2 plus ion. And so that's what's happening here, is the color has changed, which is a really good indicator that oxidation has occurred. And then what about aluminum, though? If you ever have like an aluminum spout or an aluminum drain spout or a mailbox, you typically don't see rust on there. So why doesn't aluminum rust? Well, aluminum is nice in that it gets a really pretty form of aluminum oxide that's really thin and really tough, and it prevents further oxidation from happening that would corrode and degrade the aluminum surface itself. And so that's shown here by this equation. This aluminum plus oxygen yields aluminum oxide. Alright then, what about silver? If you have silver can definitely tarnish. That reaction is typically the reaction between silver and then sulfides, and those sulfides are what form the silver sulfide, which is that tarnish, that dark brown you might have seen on silver. I don't really own much silver, but if you do, that's the silver color that you see here. And if you ever wanted to clean your silver, because you noticed it was all starting to look tarnished and no longer that nice pretty silver shine, what you can do is you can take your tarnished silver plus a little aluminum plus some hot water and some baking soda to help the reaction proceed, and you can just wait, and with time your silver will start to get reduced from the silver plus to the silver 0. At the same time your aluminum will get oxidized, and so basically you're sacrificing your aluminum. But if it's like aluminum foil, who cares? You'll start to see the brown forming on the aluminum foil, and the silver will start to get clean. Yay, science! Alright, what about explosives? Explosives basically are any time that you've got a massive redox reaction, typically that occurs super fast, followed by a very large increase in volume. And it's that increase in volume, that rapid expansion, that creates the mayhem that you see in this picture. Alright, so let's look at TNT. We've all heard of TNT, right? So with TNT, these are one of these two processes is typically what happens. They're very similar. But the idea here is you've got a solid that's producing a whole bunch of products. So one big molecule that's breaking down, and it's breaking down rapidly. But when it breaks down, notice most of these are gases. And if you think back to what we learned about solid, liquids, and gases much earlier in this textbook, solids, small volume, gases, they expand to fill their container. Well, when they don't have a container and there's a whole bunch of them competing for the same space all at once, boom! Alright, this reaction is 1,000 times expansion. So the space that was taken up by the solid has now been expanded 1,000-fold. So with that expansion comes a whole bunch of energy, and that's the destructive force of TNT. Another one you probably heard of is nitroglycerin. Alfred Noper was the one that really worked on stabilizing nitroglycerin. So he meant to be used mainly for mining, but it was also used for a whole bunch of detonation in war times. This paper was published premature to his death, and when he opened up the newspaper and saw this headline, he realized, oh, man, I'm going to be remembered for creating this destructive material and not for anything good. And so it's because of this headline that it's said that he made the Nobel Peace Prize. He wanted his name to be associated with something positive and not just the fact that nitroglycerin has killed so many people. Something else interesting about nitroglycerin is that sometimes it's called glyceryl trinitrate, and it's called that whenever you're trying to disguise what it is. And he ended up having to take some nitroglycerin to help with his heart, as heart medication before he died. And so they call it that glyceryl trinitrate just to tell people, no, we're not actually injecting you with nitroglycerin, when actually we are. It's just nitroglycerin is a really interesting molecule that can be used both in explosives and detonations, and also to help with different heart malfunctions. So with that, go read some of the other interesting applications of this redox reactions in your textbook in sections 8.5 and 8.7.